Let's start with a number, 3 minutes. That's how long npm install takes on a typical midsize Node.js project. 800 packages, a 60 megabyte node_modules folder, dependencies downloading one by one from the npm registry. 3 minutes, every single CI run, whether you changed one line of application code or you changed 800 files. Now multiply that by your team's throughput. 50 pull requests a day is not unusual for an active engineering team. 50 runs times 3 minutes is 150 minutes, 2.5 hours of pure, undiluted waste. Every day. The packages haven't changed. The log file hasn't changed. Your CI is downloading the exact same bytes it downloaded yesterday, and the day before, and every day for the last 6 months. This is the problem that GitHub Actions caching exists to solve, and solving it is not complicated. 5 lines of YAML. That's the entire fix. We're going to spend this chapter understanding exactly how those 5 lines work, because when you truly understand the mechanism, you'll be able to apply it to any language, any package manager, any CI pipeline you ever work with. Caching is one of the most fundamental ideas in computer science, and its core insight is almost embarrassingly simple. If you've already done expensive work, and the inputs to that work haven't changed, you don't need to do it again. Just store the result and hand it back the next time someone asks. Applied to CI pipelines, this translates directly. npm install is deterministic. Given the same package lock.json, it produces the same node_modules every single time. So why compute it fresh on every run? The first time you run with caching enabled, you download all your packages and then save the result to a cache store. The second time, assuming your log file hasn't changed, you skip the downloading entirely and just restore the saved directory in about 18 seconds instead of 3 minutes. The third time, same thing. The fourth, same thing. The only time you re-download is when your package lock.json actually changes, which might happen once every few days. Everything else is instant. This is not a trick. It's not an approximation. It's mathematically guaranteed to be correct because the cache key is derived from the content of the log file itself. One thing worth emphasizing immediately, GitHub Actions caching is not npm specific. The caching system stores any directory you point it at. This means every major language ecosystem gets exactly the same benefit. Node.js projects can cache node_modules directly or the npm package download cache at ~.npm. Python projects using pip can cache the pip download cache at ~.cache/pip, or cache the entire virtual environment directory. Java projects using Maven can cache the local repository at ~.m2/repository, which is where Maven stores every JAR file it has ever downloaded. Gradle has its own cache directories. Go projects cache the module download cache and the build cache. Rust projects cache their crates registry. The pattern is identical for all of them. Find the directory your package manager uses to store downloaded artifacts, point the cache action at it, give it a key derived from your log file hash, and watch your build times drop. The cache is stored on GitHub's own infrastructure, which means restore speeds are dramatically faster than downloading from the internet. You're pulling from a data center instead of traversing the public internet. Every time the cache action runs, it looks up your key in GitHub's cache store and gets exactly one of 2 outcomes, a hit or a miss. A cache hit means GitHub found an entry that exactly matches your key. It downloads that saved directory and restores it to the path you specified. Your subsequent steps npm install, pip install, whatever either skip entirely or run in seconds because all the files are already there. A cache miss means no matching entry was found. Your install command runs in full, downloading everything from the internet. But here's the part that makes the whole system self-healing. After the job finishes successfully, the cache action automatically saves the result under your key. So the very next run, the one after the miss, will be a hit. This means a cache miss is not a failure. It's a one-time investment. You pay the full install cost exactly once for each unique log file state, and then every subsequent run with that same log file gets the cached result. If you're looking at your CI logs, you'll see either cache restored from key, node Linux A3F89BC1D4 on a hit, or cache not found for key, node Linux A3F89BC1D4 followed by the install output on a miss. The action/cache action has exactly 3 inputs you need to understand to use it effectively. Everything else is automatic. The first input is path, which directory on disk should be saved to and restored from the cache. This can be a single path like node_modules, or it can be a multi-line list of several directories if you want to cache multiple locations at once. The second input is key, the unique identifier for this cache entry. If GitHub finds an entry in the store with this exact key, you get a hit. If not, you get a miss, and at the end of the job, GitHub saves the result under this key. The third input is restore keys, a fallback list of key prefixes, tried in order if the exact key misses. This is what gives you a partial hit when your log file changes slightly. We'll dig into all three of these in much more detail in the intermediate section, but for now, the mental model is, path tells the action where to look on disk, key tells it what to name the cached entry, and restore keys gives it a fallback plan when the exact name isn't found. Let's make this concrete with a real before and after measurement. We're talking about a Node.js project with 847 packages and a 62 megabyte Node_modules folder, running on an Ubuntu latest GitHub hosted runner. Without caching, here's the timeline. Checkout takes about 4 seconds, npm install takes 3 minutes and 2 seconds, that's where all the time goes, and the test suite takes 45 seconds. Total, 3 minutes and 51 seconds per run. With caching and a cache hit, the timeline looks completely different. Checkout, 4 seconds, same as before. Cache restore, 18 seconds. npm install still runs, but it verifies against the already present Node_modules and finishes in about 2 seconds. Test suite, 45 seconds, unchanged. Total, just over a minute. You've cut the pipeline time by more than half, and that savings compounds. 50 pull requests a day, each one saving 2.5 minutes, adds up to more than 2 hours of runner time saved every single day. At GitHub's hosted runner pricing, that's real money. More importantly, it's real developer time. Feedback loops that used to take 4 minutes now take just over 1. Faster CI means faster iteration. Faster iteration means better software. Now we go deeper. The cache key is the heart of the entire system, and designing it well is where the real engineering lies. A key that's too generic, just the string node modules, means you'll get hits even when you shouldn't, potentially restoring stale or incorrect packages. A key that's too specific, including something that changes on every run, means you'll never get a hit and you've added complexity with no benefit. The sweet spot is a key that changes exactly when and only when your installed packages actually change. The hashfiles function is how you achieve this. It computes a SHA-256 hash of one or more files and embeds that hash in your key. When the file changes, the hash changes, the key changes, and you get a cache miss, which is exactly correct behavior, because your packages need to be reinstalled. The ** glob pattern in hash files */packagelock.json handles monorepos automatically. It finds every packagelock.json anywhere in the repository tree and combines all their hashes into a single fingerprint. Including the operating system via runner.os in your key is critical because native npm packages compile differently on Linux versus macOS versus Windows. Sharing a cache between different operating systems would cause subtle and maddening failures. Here's the scenario: your team just added 2 new packages to the project. npm install now needs to download 2 additional libraries, but the other 845 packages are completely unchanged. With a perfect exact key strategy and no restore keys, you'd get a cache miss and re-download all 847 packages from scratch. With restore keys, you get something much better, a partial hit. The cache action first tries your exact key, the one with the full lockfile hash. That misses, because the lockfile changed. It then tries the first restore key prefix, which in a typical setup would be just node linux - no hash. It finds the most recently saved cache entry whose key starts with that prefix. It restores that entry, giving you 845 of your 847 packages already in place. npm install then runs and only downloads the 2 new packages, finishing in seconds instead of minutes. Then, at the end of the job, the cache action saves a brand new entry under the new exact key. The next run will be a perfect hit. The restore keys fallback is not just a nice to have on large projects with frequent dependency updates, it's the difference between a 30-second install and a 3-minute install every time someone touches the lock file. For Node.js projects specifically, you don't need to write the cache step at all. The official actions/setup node action has had a built-in cache parameter since version 2, and it handles everything automatically. When you set cache to npm, setup node configures the cache path, key, and restore keys using exactly the right patterns. It caches the npm package download cache at ~/.npm, uses the packagelock.json hash for the key, and includes the OS. You get all the benefits with 1 line instead of 6. The same pattern applies for yarn, set cache to yarn, and for pnpm. There's one important subtlety worth knowing: setup node with cache npm caches the npm download cache, not node_modules itself. This means npm install still runs on every job, but it completes in a few seconds because it's resolving packages from the local cache rather than downloading from the internet. If you want to cache node_modules directly and skip npm install entirely on cache hits, you'll need the manual action/cache approach plus a conditional that skips the install step when the cache hit output is true. Both strategies work. The setup node shorthand is simpler, while the manual approach gives you finer control. Understanding cache scope prevents a lot of confusion. GitHub Actions caches are stored per repository, but access is branch-aware in a deliberate way. When a job runs on a pull request branch, it first looks for cache entries saved from that same PR branch. If none exist, which is typical for a brand new branch, it falls back to looking for entries from the repository's default branch, usually main. This fallback is what makes caching so effective for PRs. Even on a brand new feature branch, the first CI run benefits from the warm cache that main has been building up over time. What doesn't work is cross-contamination between arbitrary branches. Feature/login cannot read feature/auth's cache, only its own branch cache and main's cache. Fork pull requests are the most strictly isolated case. When someone forks your repository and opens a PR, their workflow runs against your base repository's code but with zero access to your cache store. This is a security feature. A malicious actor cannot read your cached artifacts or poison your cache through a fork PR. Forks operate in complete isolation. GitHub gives every repository 10 GB of cache storage, shared across all branches and all workflows. For the vast majority of projects, this limit is essentially invisible. A Node.js project might accumulate a few hundred megabytes across a handful of cache variants, and even a Java monorepo with Gradle rarely pushes past 2 or 3 GB. When you do hit the limit, GitHub handles it automatically through LRU, least recently used eviction. The cache entries that haven't been accessed in the longest time get deleted first to make room for new entries. Separately from the size limit, GitHub also evicts any cache entry that hasn't been accessed in 7 days, regardless of how much space is available. This keeps the cache store clean and relevant. The practical implication is that if you have a rarely used branch or an infrequent workflow, its cache entries will expire between runs. You can view your repository's current cache usage and delete individual entries through the GitHub Actions UI at github.com/your-org/your-repo/actions/caches, or programmatically using the GitHub CLI with the ghcachelist and ghcachedelete commands. The real power of caching emerges when you combine it with GitHub Actions' parallel job execution model. Consider a typical CI pipeline. You install dependencies, then run unit tests, end-to-end tests, a linter, and a type checker in parallel. Without caching, each of those 4 parallel jobs runs its own npm install. You're downloading packages 4 times simultaneously, burning runner minutes 4 times over. With the right caching strategy, you install once and restore everywhere. The pattern is to have a dedicated install job that runs first, installs all packages, and saves to cache. Then all your downstream jobs, test unit, test e2e, lint, typecheck, declare a needs dependency on the install job and restore from the same cache key. Because the key is deterministic, derived from the lockfile hash, all 5 jobs compute the same key and the downstream jobs all get cache hits. You've gone from 4 npm installs to 1. The timing improvement is not just in the install step itself, it's in the total parallel wall clock time. Your test suite that used to take 6 minutes end-to-end might now complete in 3.5 minutes because the parallel jobs start meaningfully faster. When you move beyond a simple single-service Node.js project into the territory of monorepos, matrix builds, and multi-language pipelines, cache key design becomes an engineering discipline in its own right. The fundamental principle is that your key must capture every dimension along which cached artifacts can differ. Operating system is the most obvious dimension. A native Node.js add-on compiled for Linux will segfault on Windows. Always include runner.os in your key. The language runtime version is the next dimension. Some packages behave differently across Node.js major versions, and binary packages compiled against the Node.js v18 ABI are incompatible with v20. When you're running a matrix build across multiple Node.js versions, include matrix.node version in the key. In a monorepo, the lockfile hash should be scoped to the specific service whose dependencies you're caching. If your API service and your dashboard share a monorepo but have separate package.json files, use hash files, apps/api/packagelock.json, for the API cache key and hash files, apps/dashboard/packagelock.json, for the dashboard cache key. Mixing them together means a dashboard dependency update invalidates the API's cache, which is wasteful and incorrect. Each additional dimension in your key multiplies the number of distinct cache entries your repository maintains, so add dimensions thoughtfully only when the cached artifacts genuinely differ along that axis. Cache poisoning is an attack where malicious content is inserted into a cache, causing future consumers to load and execute that malicious content. In the context of GitHub Actions, the risk is real but manageable if you understand what should and should not be cached. The golden rule is, only cache content whose source is a trusted public registry. NPM packages come from npmjs.com, Maven jars from Maven Central, Python packages from PyPI, Go modules from the module proxy. These are all content addressed, checksum verified, and immutable. Caching them is safe because you can verify their integrity against the lock file. What you must never cache is build output, your compiled application code, your bundled JavaScript, your coverage reports, your dist directory. These are artifacts that your pipeline produces, not artifacts it consumes as inputs. If a malicious actor on an internal branch manages to save a Trojanized dist folder to the cache, and a subsequent run restores that cache and ships it to production without rebuilding from source, you have a supply chain attack. GitHub's branch isolation partially mitigates this. Fork PRs cannot write to your cache, but internal branches can. The defense is simple: never include output directories in your cache path. Cache inputs, not outputs. GitHub hosted caching via Actions/cache is the right choice for the vast majority of teams, but it's not the only option, and understanding the alternatives helps you make an informed decision as your scale grows. The Actions/cache approach gives you zero infrastructure to manage, a 10 GB limit that's sufficient for most projects, 7-day TTL, cross-branch reads from main, and restore speeds that are much faster than public internet downloads. Its limitations are the 10 GB ceiling, the 7-day TTL that can miss very infrequent workflows, and the fact that restore speed is still bounded by network throughput to GitHub servers. Self-hosted runners with a local disk cache are the next step up in performance. When your runner has a fast local SSD and you pre-populate it with your dependencies, restore time drops to the millisecond range. You're literally just reading from a local disk. The trade-off is that you now need to manage runner infrastructure, handle runner pool sizing, and ensure that jobs that need a warm cache are routed to runners that have it. Artifact-based caching, uploading with Actions/upload artifact and downloading with Actions/download artifact is a third approach that works across repositories and has no TTL limit, but it lacks the key fallback system and is slower than the cache API because artifacts are compressed zip files that must be fully transferred before extraction. You cannot improve what you cannot measure, and cache effectiveness is no exception. The Actions/cache action exposes a cache hit output that you can read in subsequent steps. It's a string that equals true on a hit and is empty on a miss. By logging this output and collecting it across runs, you can compute your cache hit rate, the percentage of runs that restored from cache rather than re-downloading from scratch. A hit rate above 80% is the target for a healthy caching setup. This is achievable on most projects because log files don't change that often, maybe once or twice a week for an active project. If your hit rate is below 50%, something is wrong with your key design. Common culprits include a key that incorporates something that changes on every run, a timestamp, a commit SHA, or a counter, or a log file that includes dynamically resolved version ranges that produce different hashes even when no package is actually changed. The fix is always to make the key more stable by tying it to something that changes exactly when and only when the installed packages actually change. You can also make npm install conditional on a cache miss by checking the cache hit output in an if expression, which means on a perfect hit, you skip the install step entirely, not just accelerate it. Time to test your understanding with a scenario that gets at the very core of how cache keys work. The setup: your workflow uses the cache key node runner os hash file ** package lock.json. A developer on your team runs npm install React at 19 to upgrade from React 18 to React 19. npm updates the package lock.json to reflect the new version and its updated dependency tree. The developer commits and pushes. What happens on the next CI run? Let's trace through it precisely. The hashfiles function reads the packagelock.json file from the repository, computes its SHA-256 hash, and embeds that hash in the cache key. Because the lock file content changed, React 19 has different dependency entries than React 18, the hash changes. A completely different hash means a completely different cache key. When the cache action looks up this new key in GitHub store, it finds nothing, cache miss. npm install runs in full, downloads React 19 and its updated peer dependencies, and populates node_modules. At the end of the successful job, the cache action saves the new node_modules state under the new cache key. The very next run, which will have the same log file, will compute the same hash, find the exact same key in the store, and get a cache hit. The system is completely self-correcting. This is the elegance that hash files makes possible. Cache invalidation is automatic, content-driven, and requires zero manual intervention.